This is Chapter 9, Test Addition Review. We're going to look at some things that we did in Chapter 9 to help you review for the add-on quiz that we are taking tomorrow. In Chapter 9, we studied exponents, and we started off with problems like 2 to the third power and what that really means. And 2 to the third power would mean 2 times 2 times 2, writing out 2 3 times, and we'd multiply 2 by itself 3 times. So the flip side of that, if we had 7 times 7 times 7 times 7 times 7, and we were required to write that with an exponent, we would leave our base 7, and we would count 1, 2, 3, 4, 5 times that we're multiplying it, so our exponent would be 5. So we'd write 7 to the 5th power. Also, with exponents, we might be asked to evaluate. So we are going to evaluate. That means find the value of. Evaluate 3a to the 4th power if a would equal 5. So what that means is we're going to take the 5 and plug it in here for a, and we would write 3 times 5 to the 4th power. So to evaluate this, we'd follow PEMDAS, and PEMDAS says you would do exponents before you multiply. So we would write 3 times, and we would have to evaluate 5 to the 4th power. That means 5 multiplying by itself 4 times. So to quickly multiply this, I would say, well, the first 5 times 5 is 25. And the second 5 times 5 is 25. And if I took 25 times 25, I know that would be 3 times 625. And I can multiply 3 times 625 then for my last step and have 1,875. So I have evaluated 3a to the 4th power. Next, we went on and we looked at some other things with exponents. For example, multiplying when they had the same base. So 3 to the 4th power times 3 to the 8th power, you leave your base of 3 and you add the exponents 4 plus 8, so it would be 3 to the 12th power. You could have a variable, let's say x to the 4th power times x to the 3rd power. You would say x to the 4 plus 3, so x to the 7th power. Well, if we threw coefficients in there, so let's say we're going to take 2y to the 4th times 3y to the 5th. The 2 and 3 are not the same bases, so we have to actually multiply. This is a multiplication problem, and 2 times 3 would make it 6. And then y is the same base, and we would add the exponents of 4 plus 5, so 6y to the 9th power. We also talked about division, so we might have something like x to the 8th over x to the 3rd. And when it's the same base, you leave that base of x and subtract 8 minus 3, so x to the 5th power. So we did multiplication with the same bases, we did division with the same bases, and then we also did what is called monomial multiplication, where you actually multiply numbers that are not the same bases, but still adding exponents of like bases. We went on then to talk about power of powers. Okay, power of powers. And power of powers just means that you would have something like x squared to the 3rd power. Well, when that's the case, you actually multiply these because it's saying taking x squared 3 times. That would make it x to the 6th. If you had 5 squared to the 5th power, you would leave that base of 5, and 2 times 5 is 10, so 5 to the 10th. And finally, if we had 2x to the 3rd power, that just means you need to take 2 to the 3rd power and x to the 3rd power. And 2 to the 3rd power, I can figure that out. 2 times 2 is 4, times 2 would be 8, so 8x to the 3rd power. So that would be finding the power of a power, and you want to multiply that out as much as you can when there are variables involved. All right, we're going to move on now and talk about negative exponents. Negative exponents involves 2 to the negative 3, something like that. You cannot leave negative exponents on a base. So if I had 2 to the negative third power, that involves putting a 1 over 2 to the third power. When you bring that to the denominator, it changes the exponent to a positive. It doesn't change anything else other than that exponent. So if I had 8 to the negative fourth, that just means I'd have 1 over 8 to the fourth power. So that is removing negative exponents. Moving on to scientific notation, if you had to write in standard form is just writing a number like a regular number. So let's say we had 2.7 times 10 to the fifth power. What that would involve is taking 2.7 and moving the decimal 5 places. When it's a positive number, you move that decimal 5 places to the right. 1, 2, 3, 4, 5. Filling those empty waves with zeros. Then I'd write my 27 and my 4 zeros and go back and put my commas in. 270,000 would be the result. Next, let's try one where I have 2.7, and this time I have it to a negative exponent. Let's say negative 4. So if I take my 2.7 away from it, the negative 4 means I'm moving my decimal to the left 4 places. So 1, 2, 3, 4. Again, in my empty waves, putting in zeros. So my number would be 0.00027, a very small decimal. When it is a negative exponent on that scientific notation, it is a very small decimal. All right, let's move on. We're going to take scientific notation to a new level. We're going to take 3.2 times 10 to the 7th, and we're going to add it to 2.1 times 10 to the 5th. Well, the thing is, you can't add numbers that have different exponents in scientific notation. So I have to take my biggest number with biggest exponent in scientific notation and rewrite it so that it has the same exponent. So here's what I would do. If I have 3.2 times 10 to the 7th, I'm going to continually move my decimal over until my exponent becomes a 5. So when I move it once, a 32 now, that becomes an exponent of 6. Move it one more time, 320, that then becomes an exponent of 5, and that's perfect. That's what I want. So my numbers now are really 320 times 10 to the 5th. I'm adding it to 2.1 times 10 to the 5th. When they have the same exponent, I can take the numbers and literally write them and add these two together. 320 plus 2.1. Being careful to line up the decimal. And 320, I don't see it because it's at the end. So I'm going to put a 0 in as a spacer, bring my decimal down, bring down a 1, and add 322.1, but it's times 10 to the 5th. Now 322.1 is not an acceptable scientific notation number. It has to be a number between 1 and 9.9. So I've got to move my decimal back, increasing my exponent each time I move a place. So I move it once, it becomes a 6. Move it one more, it becomes a 7. So I then have 3.221 times 10 to the 7th power. That is adding in scientific notation when they have different exponents. You've got to change them to the same exponent. Go ahead and add or subtract the numbers involved, and then take it back to a good scientific notation number. Okay, finally, we finished off with linear versus nonlinear functions. Okay, so I'm going to kind of line this up so that you can see what we're talking about. On a graph for linear, versus nonlinear, you would look for what kind of graph is placed on there. For linear, you would look for a straight line. It is linear if it is a straight line. It would be nonlinear if there would be a curve involved. So nonlinear because it has a curve. So that might be something that helps you decide, and that's the explanation. If it has a curve, it is definitely nonlinear. We also talked about equations. So for linear, it would be something that could be written in the form y equals mx plus b. If it could be written in that form, it is definitely linear. But here were the things that I told you to look for that made it nonlinear. If the equation had an exponent, it definitely is nonlinear. If the equation has the variable in a square root sign, that is nonlinear. And if it had a variable in the denominator of a fraction, all of these are considered nonlinear. You could not put it in the form y equals mx plus b. And that concludes the highlights of Chapter 9 and the kinds of things that would be on the quiz tomorrow.